Okay, so that formula that we were just using over on the other slides is just our average rate of change, which is defined to be f of b minus f of a over b minus a. This is just our slope formula, except we've tightened it up a little bit with the usage of function notation. So we're going to use this relatively frequently whenever we want to talk about how much a function is changing with respect to how much our x variable is changing. And for the last one, our x variable was time. So when we look at position in comparison to time, we're talking about velocity. So for instantaneous speed, if you remember, we need to measure the change in position versus the change in time. But the larger the time interval that we use, the less accuracy that we have. So we need to take this change in time or change in our variable to be very, very small. But we can't take that to be zero because, well, nothing moves if you don't change anything. But how small? So the best we can do is find an estimate of instantaneous speed by taking things over a smaller and smaller time interval. So if we took our time interval to be, say, 1/1,000,000th of a second, yeah, we would get a very accurate measurement of speed, but it would still be an estimate. So we need a way to take a variable as close as possible to zero. And I do mean as close as possible, not 1/100th close, not 1/1,000,000th close, but pretty much right on top of zero without it actually being zero. And this is where the nuance of calculus comes in. So for functions that we consider continuous, which is an idea that we're going to revisit and come back to pretty frequently, there's no real difference between the limit of what a function is going to and the function value itself. So if you have just a regular old function, it's nice and connected, it doesn't have any holes or anything weird, and you want to talk about, okay, what's the limit of the function as my x value approaches a? Well, you don't really need a limit. That would be way too much because we can see on the graph that's a defined value right there. So we don't really need the language of limits to be able to talk about that. What limits help us do is they help us understand a function's behavior in places where the actual function value may not exist. And you may be thinking, well, how is that useful for me? Well, you've already done it. In college algebra and in pre-calc, you looked at something called a horizontal asymptote. A horizontal asymptote is actually the limit of a function as x approaches infinity. So like if we talk about x squared, for instance, you would call that in behavior. So a more mature way to say that would be as x goes to infinity, f of x equal to x squared also goes to infinity. So let's talk about a little bit of notation so we can really start to fine-tune our ideas of a limit. Now, sometimes a function's behavior might be different depending on which side of the value we are approaching the limit from. So we break our limits down into one-sided limits at first, and the first one we're going to take a look at is this right-handed limit. So the right-handed or right-sided limit of f of x as x approaches a, we write that as the limit as x goes to a with that little plus sign there. And that little plus sign indicates that we're coming at a from the right. And we say that that limit equals L if it exists. So the reason why it gets that plus sign and we're talking about things from the right is because if we take our number line and we take a look at a, for instance, a can be any particular value. If we're looking at coming at it from the right, which is over here, then we're looking at values of x that are greater than a. And we should probably take out that little equal sign there because we can't actually plug in equal to a. But that is what the right-hand limit means. It's what the function is doing as x is getting really, really close to a, but still greater than a. So like if a equals 2, we would look at maybe f of 2.1, maybe f of 2.01, and just inch up closer and closer to where we want to go. So for instance, the limit of 1 over x as x approaches 0 from the right would be infinity. And how we would write that would be the limit as x goes to infinity, so we get to play with infinity now, that's fun, of 1 over x equals infinity. And there's a couple different ways that we can verify that. Number one, if you look at the graph of 1 over x, as x gets closer and closer to 0, and I've made a little mistake here, so that should read as x goes to 0 from the right. There we go. Everything looks good now. So that means that we're kind of following our function along, and our x equal to 0 is right here. So we're taking x and we're following our function as x gets closer and closer to 0. And it looks like it just shoots up with no limit on it or anything. So functions that increase without bound, so that means that it's just getting larger and larger as we plug in values of x that are closer and closer to 0. So if we plugged in, you know, f of 0.1, that would be 1 over 0.1, because we have 1 over x, so that would be 10. And I say, well, maybe that's not close enough. Maybe I want a little bit closer. Then we'd have, let's say, f of 0.001. Well, 1 divided by 0.001 would be 1,000. And if we took it even closer still and said, well, what about f of 0.0001? That would be 10,000. So based off that information, as we get closer and closer to 0 from the right, our function values are just going straight up. There is no rhyme or reason to the values, but they are increasing, and they're increasing rapidly. They're not tending towards any particular value. They're just getting really big. So when you increase without bound or without a ceiling, that would be an infinite limit. So we would say that that limit's going to infinity. So similarly, if we can have right-handed limits, we can have left-handed limits. And it's for a pretty similar reasoning here on a number line. Wherever your value of a is, if you're coming at a from the left, then you're taking all these x values to the left of a and just inching them closer and closer to a. So all of these left-handed limits, they're going to be using values of x that are less than the value that you want to look at. So going back to our 1 over x, if you notice to the left-hand side of that graph, so we just talked about what it does up here, to the left-hand side of that graph, we shoot all the way down like that. So it might be reasonable at this point to say, hey, that just looks like it's going straight down. It would be reasonable to say that that limit is negative infinity. So let's talk about that in a mathematically mature fashion here. So the limit of f of x as x goes to 0 from the left. So this is what our x value is headed towards, and this whole expression represents what f of x is doing as x gets closer and closer to 0 from the left there. So just kind of following along our function, as x gets closer and closer to 0, our function just drops straight down towards negative infinity. Now, if we wanted a bit more scientific approach to this, other than, hey, just, look at this graph, what we could do is we could say, well, okay, what's f of negative 0.01? So pretty close to 0. That would be negative 100, 1 over negative 0.01. And say, well, okay, let's move even closer. How about f of negative 0.001? That would be negative 1,000. And then closer still, if we wanted f of negative 0.0001, that would be negative 10,000. So similar pattern to what we saw before. We have this number that's just getting lower and lower and more negative. It doesn't look like it's headed towards any one value in particular. So that's why we would get to say at this point that, yeah, our limit looks like negative infinity. Negative infinity isn't a value that you can plug in, at least not now. But when we write negative infinity, what we're saying is that our function is decreasing without bounds. So it's just going down and it's not stopping. It just is going to keep going. So that's when we use negative infinity.